Measures of variability provide us with a way of describing the amount of spread, the amount of variation, distribution that we have inside our data. In this section, we'll have a look at a number of common techniques that we can use to measure that variation. So as we said, it provides us a way of quantifying, of attaching a number to the degree of spread or dispersion across values inside a data set. It's particularly important because our usability tests are going to involve users, and for many things users will have a range of views or opinions. They're not all going to be the same, so we can reasonably expect that there will be variation whenever we survey our users, and we want to understand then the extent of that variation, to understand if there's a wide range of views or if actually users are mostly of the same opinion about some particular aspect. So they give us, the type of measures we're going to look at here, they give us a way of quantifying that, of attaching a numerical value to it. So if we're running multiple different tests, we can then more meaningfully ask and look at across those tests in terms of the amount of variability that we see. It gives us the tools then to do those types of comparisons. We're going to explore really, well, it's three: range, variance, and standard deviation. Although, to be honest, range and standard deviation are the real sort of metrics that we would have an interest in using. We'll start off first of all with the range. The range is quite simply the difference between the smallest and biggest value. That's it. That gives you your range. So it's the distance over which the values range inside the population. It can provide us with the useful tool then for identifying outliers. So if I give you some data and I also say there's the range of that data, you can ask, does that meet expectations? And if it doesn't, then it may be an indicator there are a number of outliers that are not what was anticipated. And again, you can then look at those outliers and think about, well, what do we do with them? Are they valid? Are they just erroneous aspects collected through the experiment? Variance then is a more interesting one. And variance, it tells us how spread out the data is, and that's relative to the mean. So we're going to have here our mean value, the arithmetic mean, the average, and variance is going to be a measure that tells us how spread out the data is relative to that mean value. And I could almost ask you to do this as an experiment. I could say, okay, here's some data, here's the mean value, come up with some metric or some mean then that gives you a value, and the bigger that value is, the more spread out the data is away from the mean. And there's lots of different ways you can do it. Variance then is the standard way of doing it, and we'll have a look at it here. It consists of 3 steps. You can see that in the bullet points that we've highlighted here. In the first one, each value is subtracted from the mean, giving the distance from the mean itself. Now, that kind of makes sense. Let's think about this here. So over on our table of data, we've 8 users who have collected timings across a number of the tests. We've calculated the mean, and that's 22.9 for this particular type of data. So the first step we're going to do is to take each of the user values and to subtract that from the mean. That gives us the distance from the mean. And if you think about variance, that's what we're trying to measure. We're trying to come up with a value that describes, are values closely situated around the mean, or are they spread far apart? What's the overall distribution? So calculating the distance from each value to the mean is a really important step. The second bit then, each value is then squared. That has 2 effects. The first thing is it makes sure we're always dealing with positive numbers. So if a value was 2 less than the mean and the difference was -2, if we square it, we get 4. So we always end up with a positive value, and we amplify the distance that things are away from the mean. So if something's quite close and we square it, it'll be a small number. If something's quite far away and we square it, it's going to turn into a correspondingly bigger number. So that amplifies the overall distance that we have away from the mean. The third step that we then do down here is the mean of the squared values is then calculated. So that simply says, okay, so in this case we had 8 values. We've calculated their distance, we've squared it. Let's just take the average value that we have then. And that average value is what we call variance. So it's just simply a common sense, logical way of measuring, on average, the distance that we have values away from the mean, or rather the square of the distance. You can see down here, here's the typical equation that we have for calculating variance. And the parts of this are just what we talked about. So over here we have each value xi, and we're going to look across from the first value to the last value. In our case, we have a total of 8 different values that we're putting through this. We're taking away from each value the mean. So we're taking away 22.9 in this particular case. So xi minus the mean of x is basically step 1. We do that. We then square that, which is step 2, and we're then going to calculate the mean. So we add them all up and we divide them by the number, or nearly the number. So it's n minus 1 as opposed to n. And whilst variance is actually quite a straightforward measurement, there is this one little gotcha that we've encountered here. The rest of it all makes sense. Take the value, take away the mean, square it, add them all up. Why are we not dividing by n? Why are we dividing by n minus 1? The reason for this is a subtle point. It ties into the difference between statistics for a sample and statistics for a population. So when we're talking about, which is really just parameters, so when we're talking about a population, so that's all users, and we ask what is the average value, that is going to be notionally a definitive value for that population. It's going to be a parameter of it. So that if you, for example, could freeze time, because, for example, if you think about height, people's height changes over time, but if we take a snapshot in time and we go through every single person and we take all of their heights and add it all up and take the average, we will get the average height, and that will be a parameter of that population. If we then take a sample of people, I've got 100 people, and I take, again, freeze time because they'll be growing and changing, I take their heights, I will get the average for that sample. Now, the bigger the sample is, the more likely it is going to map onto the population's parameter. It's going to be an accurate reflection of it. The smaller the sample is, then less risky, or the more risky it is that we may do that. So there's a small gotcha in this case here. When we are dealing with samples, which we are, we don't divide by the number, we divide by n minus 1. That's how we calculate our overall variance. And you can see down here that if we were dealing with a full population, all of the values that we have inside the population, we calculate variance just as we've described. Take each value away from the mean, square it, add them all up, and then divide by the number of values. So that's the only small gotcha in this, but beyond that, variance is quite a meaningful, straightforward measurement. Standard deviation then is simply the square root of variance. That's it. You take your variance and you take the square root of it. And if you think about it, that kind of makes sense, because when we were calculating the variance, and the bit underneath the square root is what we have calculated, each value taken away from the mean, squared, added all up, and then divided by n minus 1 because it's a sample from a wider population. That gives us the average squared distance away from the mean value. If we take the square root of that, we get the average distance away from the mean. And that's what standard deviation provides. Thankfully, if we take the square root, it means that the units become the same. If we're talking about a measurement, in this case, for example, in seconds, and we calculate the standard deviation, our standard deviation is in units of seconds. The units remain the same whenever we calculate the standard deviation. And you can see an example over here in our table where we've calculated things where we've got our variance, then we've got our standard deviation of 5.5 compared to our mean of 22.9. Now what that means, the standard deviation then of 5.5, is that if I just say, here's a value at random, another value, and you were to say, okay, typically, I know my mean, my 22.9, typically for a random value you've just given me, how far away from the mean should I expect that value to be? And 5.5 is the measurement we've ended up there. On average, it'll be 5.5 away from our mean value, be it above or below, but that's just the typical one. And if we had another population and its variance or standard deviation was say 2, we know that if I give you another value, it's much more likely than it's probably going to be sort of 2 away from the mean. So it's a really useful measurement then to let us understand the spread of values that we have in a population relative to that mean. One of the small things in the inside, and this is actually quite important, depending on the size of the sample, so bigger samples are better because it's less subject then to sort of individual values. But if you have a large outlier, so a large positive value, anything we're dealing with will be large positive, don't really have large negatives, that will tend to have a disproportionate effect on certainly the variance. So we need to be slightly cautious then whenever we're dealing with large outliers that they can have a heavier effect in terms of our measures of variability. In terms of Excel then, how we can calculate these different activities, if we're thinking about the range, we have the minimum and maximum functions. You simply pass in a list of values and it'll tell you the min or max value in those. Fair enough. If we're dealing with variance or standard deviation, we have 2 types. So we have var.s and var.p, standard deviation stdev.s and stdev.p. The .s and the .p are the different versions of this if you're dealing with a sample, the .s's, or if you're dealing with the full population, the .p's. In all of our cases, because we will be dealing with a sample of users that we have collected, we will want to use the var.s and the standard deviation.s. That's the particular ones that we use. If we're looking at the stdev.p for the full population, it's the versions of the equations. We're not dividing by n-1, we're just dividing by n. Doesn't really make a meaningful difference if we've got a large sample size, but sometimes we won't have a large sample size, so we should use the appropriate function here. So that's all we want to cover inside our measures of variability. It's really quite important because quite often we will want to understand how much variability we're observing inside our data. Ranges do provide us with a good, easily calculated way of doing it. We should also then calculate our standard deviation if our data then supports, as interval data where we can calculate these different types of activities. We should calculate then our standard deviation so that we understand how much spread we're seeing inside our respective measurements. After this, we're going to go on to have a look at confidence in terms of how we can mathematically, statistically attach a confidence value then to our findings, so that if we say the mean is this, we can also say how certain we are that the mean is this based on our population size and our sample size that we're dealing with inside that.